those video series are in regards to magnetic force. So what we will see as subtopics for this will be how a charged particle is interacting, that is moving, is interacting with a magnetic field. What are the differences and what we see when the mass is changing, or when the speed is changing, or when the charge is changing, and all that stuff. And then we will move to the velocity selector and the mass spectrometer, which are pretty much the applications of the dynamics of the moving charged particle into a magnetic field. So we'll start first with the concept of a particle moving into a magnetic field. Let's suppose that we have a particle, either a positive or negative, doesn't really matter. For now, I will say that the charge is negative, and then it is entering perpendicular to a magnetic field that is coming out of the page. So this is the magnetic field here. Now, based on the third law, third application of Newton, third application of the left-hand rule, we can identify the direction that the force, the magnetic force is exerting on the charge as it is entering into this magnetic field. So since we have a negative charge and we are using the left-hand rule, then the thumb will tell us the direction of the motion of the charge, and then fingers will tell us the direction of the field. So therefore, magnetic force will be perpendicular. And we know that it's perpendicular because we have said that magnetic force is mutually, or those three quantities are mutually perpendicular to each other. So magnetic force, velocity, and magnetic field strength. If two of them are not, then the third one doesn't exist. Okay, so now as you see here, the magnetic force and the velocity of the charge are perpendicular to each other. Okay, the velocity of the charge is this one here. So we have a charge that is on this direction, is moving on this direction, and we have a magnetic force that is moving on this direction. But if you recall what we have said as the condition to have a uniform circular motion from physics 20, and if you don't, then I will post the video of the uniform circular motion that is in the relation to the physics 20. When we have the fact, the condition, the situation in which the velocity is perpendicular to magnetic force, perpendicular to each other, then what the object is obtaining, the type of motion that the object is obtaining, is uniform circular motion. Okay? Now, for what we are seeing here, the force, magnetic force, is way greater than force of gravity. So therefore, we can easily say that in the conditions when we have charge that force of gravity can be ignored, then force net is the same as magnetic force. On the other hand, what we have said is in physics 20 is that centripetal force is not a force on its own. But what it does, it steals the identity of force net when force net is perpendicular to the velocity. So what we have here is that centripetal force, which is always mass times centripetal acceleration, or mass times v squared over r. And then there are others that we have seen in physics 20, but for purposes of physics 30, this is what we have to stop, kind of. Then centripetal force steals the identity of force net, which with the condition, or with the acceptance, with the agreement that force of gravity is way smaller than force, a magnetic force, then we can say that centripetal force steals the identity of force net. And since force net is equal to force of magnetic force plus force of gravity, but since this is too small, then we can say that force net is about equal to the magnetic force. And for what we are doing here on physics 30, you can easily say that for the range of the accuracy that we are using on physics 30, it's fine to say that force net is equal to magnetic force. So what we have now is that centripetal force, or that is now force net, centripetal force, that is always mv squared over r, or mca, AC, is equal to magnetic force, which we saw in the previous lesson, that it is QVB. Okay, so now centripetal force is equal to magnetic force, which means that it is mv squared equals to QVB. So now let's take those two relationships here. Mv squared over r is equal to QVB. So speed is cancelled out since it is the same in both sides, and then we'll have mv over r is equal to qb. So when a charge particle is entering into a magnetic field perpendicular to it, then based on the third application of the left-hand rule, we know that magnetic force is perpendicular to the velocity. And since force of gravity is way smaller than magnetic force, then we can say that force net is equal to magnetic force. And since force net is perpendicular to the velocity, that means that the object will obtain a uniform circular motion. And based on this, mv squared over r is equal to qvb. This is a relationship that I recommend you doing every time that you are dealing with a charged particle entering into a magnetic field perpendicular to it, because it is not a difficult one. And then you solve from there whatever they are looking for. So let's see. Let's suppose that we have a case that an electron is entering. So, example, an electron is entering into a magnetic field that is, magnetic field is 0.0035 Tesla, and it is in the direction into the page. The velocity of the electron is 5.20 times 10 to the power of 6 meters per second going north. And we are dealing with an electron as the charge. And let's figure out what is the radius and the path of the electron, of course. Okay, So let's draw a situational diagram of this particular problem. We have a magnetic field that is into the page, and into the page means that it is represented graphically or in the situational diagram with crosses. Okay, magnetic field is 0.0035 Tesla. Now what we have is that the velocity of the electron is north. So electron is entering. Velocity of the electron is 5.20 times 10 to the power of 6 meters per second going north. Now what is the force? Or no, yeah, what is the force based on the third rule of the left-hand rules? And that will tell us what is the way that the electron is deflected. So now the thumb will tell us the direction of the electron. We will not change it since we are using left hand and the charge of the particle is negative. So the thumb will be going north. Now magnetic field will be going into the page, so your fingers should be toward the page. Therefore, the path that the electron or the magnetic force first is this one, is on this direction, and the path of the electron as it is entering into the field will be this one here. Okay, so now what we will look for is what is the radius. Radius of the electron. Now, again, the logic is this: since magnetic force is way, way smaller than force of gravity, you can check this. Then we can say that force net is the same as magnetic force. Okay, so this is one fact. The second one is since magnetic force that is equal to force net is perpendicular to the velocity, then the charge, which is the object in our case, will obtain uniform circular motion. So centripetal force is equal to magnetic force, or mv squared over r is equal to qvb. This canceled out, and we have the relationship mv over r equals to qb. This is a relationship that, as I said, like it takes you probably less than 1 minute to reach this finding. From here, we are looking for radius. So radius will be mv over qb. Now, mass and charge of the electron are not given, but those are part of the constants in your formula sheet. So 9.11 times 10 to the power of negative 31 kilograms times the speed I said is 5.20 times 10 to the power of 6 over the charge of the electron is 1 elementary charge, so 1.60 times 10 to the power of negative 19 times 0.0035 Tesla. So enter this in your calculation, and I will do so as well, and this give you the value of the radius. What I have is 0.00845 meters, or you can say 8.45, 46 actually. It is 46. 8.46 times 10 to the power of 1, 2, 3, -3 meters. So the radius of the electron entering into that particular magnetic field is 8.46 times 10 to the power of -3 meters. Okay, I hope that this makes sense. Now let's take a look on a second example. When we are in the same field, we are entering, or two particles are enter, electron and proton, and then we will see what is happening with them. So the electron and proton are entering into a magnetic field with the same velocity. So velocity of the electron is the same as the velocity of proton, and it is 6.25 times 10 to the power of 6 meters per second going south. And what we have is magnetic field strength is 0.040 Tesla going out of the page. Now what we will do is we'll find what is the radius of the electron and what is the radius of proton, and for both of them, and then see what is the path. Okay, let's draw a situational diagram where we are showing what is the magnetic field and how they will, both those particles will deflect. Okay. So we have a magnetic field that is out of the page, and out of the page is with dots, are represented with dots. So magnetic field strength is 0.040 Tesla, and both particles, electron and proton, are entering and going south. So electron and proton, they both have the same velocity as 6.25 times 10 to the power of 6 meters per second. So let's figure out what is the magnetic force or that electron is experiencing and what is magnetic force that proton is experiencing. And actually I will do this with a different color so that we can see it. So let's start with the electron first. So we have an electron, which is a negatively charged particle entering south. So your thumb should be south. And then a magnetic field that is coming out of the page. So your fingers should be out of the page. And then the magnetic force that the electron is experiencing is starting at your palm, okay, which is going east. Now, if we are applying the third left-hander rule, then for the proton, then we have a positive charge that is entering south. So thumb will be switched now. If we are using the left hand, will be switched. So we'll go north. Magnetic field is out of the page. So your fingers should be out of the page. And then magnetic force will be to the west. So that is telling us that the path of proton is this, and the path of the electron is this. Okay, so let's find now what is the radius of each of them. Okay, again, since magnetic force is way greater than force of gravity, then force net is equal to magnetic force, you can see. Since magnetic force that now is force net is perpendicular to the velocity, then magnetic force is equal to centripetal force. So QVB is equal to mv squared over r. So V is cancelled out. QB is equal to mv over r. This is, again, the same relationship, and I'm showing you that every time that you're doing this, follow this logic, because this doesn't leave you dry on any situation. Now we are looking for radius of the electron, which means that we'll go mass of the electron, velocity of the electron over charge of the electron times B, the outside magnetic field that the electron is entering. Now, if we enter the information that we have, times velocity is 6.25 times 10 to the power of 6 over charge of the electron is 1 elementary charge, so 1.60 times 10 to the power of negative 19 times 0.040 Tesla. So the radius of the electron, enter this in your calculator, and I will do the same thing and see what it is. And what I have is 8.90 times 10 to the power of negative 4 meters. And this is the radius of the electron. Now the same logic we will do and implement and apply for the proton. So radius of the proton will be equals to mass of proton, velocity of proton over charge of proton, and magnetic field strength. So mass of the proton is 6.65 times 10 to the power of negative 27. Velocity is the same as the velocity of the electron. Over charge is 1 elementary charge is positive, 0.04. Enter this in your calculator and we will see that 6.65, 27. We will see that the radius of proton is, my bad, the mass of proton is not 6.65, it is 1.67, my bad. And then the radius of the proton when we enter it is 1.63 meters. Okay, so you see now what is the difference of the two particles in the radius of the two particles that are entering in a magnetic field with the same speed, just the mass is changing. Because see, what do we have here? We have the radius is mv over qb. So when the mass is increased, the radius is increased, is proportionally increased at the same rate. Okay, so just keep this in mind when you are looking for the radius of a particle. Okay, so now we will just do some more examples. Now what we have is a alpha particle and a proton entering with the same speed. and then we will see what is the radius of alpha and what is the radius of proton. So we have an alpha particle and a proton entering with the same velocity, 5.75 times 10 to the 7 meters per second, going into the page. And magnetic field is 0.037 Tesla, going north. Okay. And we are looking for radius of alpha and radius of proton. So again, radius is mv over qb. Now, when we are calculating the radius of alpha particle, will be mass of alpha particle, velocity of alpha particle over charge of alpha particle times b. Mass of alpha particle, let me check it on so that I don't do the same mistake as I did with the with proton, is 6.65. This is 6.65 times 10 to the power of negative 27 times 5.75 times 10 to the 7 over charge of alpha particle is 2 times 1.60 times 10 to the power of negative 19 times 0.037 Tesla. Let's enter this in the calculator and see what is the radius of alpha particle is 32.30 meters. And using the same logic, we will find the radius of the proton. So radius of proton now will be mass of proton, velocity of proton over the charge of proton, and magnetic field strength. So the mass of proton is, now we know, it is 1.67 times 10 to the power of negative 27 times the velocity, that is 5.75 times 10 to the power of 7 over charge of the proton is just one elementary charge, 10 to the power of negative 19 times 0.037, not 35. Enter this in your calculator and see what is the radius. I have here that the radius of the proton is 16.22 meters. It's about half of this. Yeah, so if we are going to draw this situation, then what we would have is a velocity of proton and electron is entering into the page. So we will have something like this. Magnetic field is going north. B, and we would have the electron and the proton and alpha particle entering into the page, is into the page, is cross, okay. Yeah, it is into the page, I think it is into the page, yeah. So now, based on the third application of the left-hand rule, your thumb will be opposite of what is happening. So instead of into the page, your thumb will be out of the page because we are using the left-hand rule, and alpha and proton both are positively charged particles. And then magnetic field is going north. So your palm will be in the going east. That tells us that the proton will have a deflection of this, and alpha particle will have a deflection that is almost double. So alpha particle and proton. Okay. That's it for the first part of this group of videos. We have dealing with the charge, the charge that is entering into a magnetic field, and we cleared that the path is a circular or part of the circle, and it is a uniform circular motion that it is obtaining. And we went through the logic of how and why, and we found the magnetic field, the radius that the particle is obtaining. Now I will present to you a question, and then you think about this on your own, so that we will discuss it even in class, this question. So what should the velocity of the electron be so that the radius of the electron is 3.84 times 10 to the power of -4 meters, while it is entering into a magnetic field that is 0.0037 Tesla. Okay, so what? Let's ignore those vector signs for now. Just go with this, and then what should, after you find that velocity, what should the velocity of a proton be so that is having the same path, okay, the same path as the electron? Okay, so first will be what is the velocity of the electron, and then you will go, what should the velocity of proton be so that it is having the same path as the electron? Okay, I will stop here. We will deal with this question in class as well, and you try it on your own, and I will go over and explain it to you in more details in class.